Yes.
Okay. Okay, thanks for having this seminar, and I'm Jiawei Wang from the Department of Civil Engineering, McGill University, and today I want to present my recent research reducing bus bunching with asynchronous multi-engine reinforcement learning. And the report will consist of 4 parts. Now let's begin with the background and motivation. According to the government report, the number of passenger trips in Canadian public transit amounted to almost 1.88 billion trips in 2019. And in Montreal, there's about 1.4 million day ridership, and such a great demand is served by over 1,000 bus fleets on over 200 bus routes. However, the public transit system is unstable in nature due to the uncertainty from imbalanced demand, traffic congestion, and other interruption. Such uncertainty will cause bus bunching, in which 2 or more buses that should evenly running along the road simultaneously arrive at the same stop. And intuitively, if a bus is slightly delayed due to the uncertainty, it has to pick up more passengers at the next stop than expected, then it will result in further delay. In this case, the passengers have to wait for longer time, and the utilization of buses will not be even, and there will be a deteriorate in the in-vehicle bus service level. As a result, the real-time control strategies are needed in transit operation to maintain regularity and provide reliable and efficient service. And according to the past review, we can identify that there are generally 2 types of bus control strategies in terms of the spatial configuration. The first is the station control strategies, and the other is the interstation control strategies. Actually, no matter which control strategies you choose, the trade-off is ubiquitous. For example, the stop skipping strategy will suggest the bus skip the stops as long as there are no line requests, even if there are passengers waiting at some bus stops. It will definitely increase the vehicle commercial speed, but it will also cause unsatisfying passenger experience. And another example is the bus speed regulation strategies will control the bus speed along the bus road. It will decrease the heavy irregularity, but it's really hard to implement in real-world operation. And according to the past review, the holding strategies is the most adaptive one because it can make a good compromise among control efficiency, manual feasibility, and service satisfactory. And for the holding control strategies, we can identify that it has 3 types in terms of their objective function. And from the recent studies, we can identify that how to incorporate real-time information to elevate the control efficiency is one of the key considerations. However, even if the private studies have suggested the transit control with the real-time information, there are mainly 3 limitations for these methods. First, they will increase the problem complexity when they consider the global information from the system, for example, the sharing control decisions of each bus, because they cannot utilize each decision as prior information. Second, their policy may be myopic or isolated because they do not consider the long-term effect of these decisions efficiently. And the last is that their policy may be static because they do not update the policy based on the real-time feedback. And luckily, the reinforcement learning has provided a new control paradigm to overcome these issues. And from the past studies, there has been a wide range of applications using reinforcement learning in traffic control, but in transit control domain, there are few studies. And according to the contribution from the research on reinforcement learning with for transit control problem, 3 stages are summarized in this presentation. At first stage, the researchers try to formulate traditional transit control problem in reinforcement setting. And at stage 2, the researchers will try to decide sophisticated frameworks on some machine learning knowledge. And at stage 3, the researchers can take a step further to incorporate the traffic domain knowledge into the advanced reinforcement learning framework. And the most studies currently are staying at stage 1, In specifically, how to define a value reward function is their major concern. However, different from other traffic control scenarios, the transit control on buses may not be implemented simultaneously. Therefore, the traditional multi-engine reinforcement is limited to handle such asynchronicity. And therefore, this study aims to design a efficient multi-engine reinforcement framework to achieve bus holding control, which can not only exploit the advantages of reinforcement, but also fix the mentioned asynchronous issues. Now let's begin the methodology. In reinforcement, and there is an intelligent engine learns to maximize its cumulative reward in the environment through the interaction. And in our problem, the buses are regarded as the intelligent engines, and the environment is treated as, and the transit system is the environment. And then we can formulate the elements in reinforcement pipeline. The first element is the state observation, which should characterize the dynamic of the system as efficient as possible for engine to derive its policy. In our study, we suggest each engine has a local state observation, and the feature of the observation includes the backward headway, forward headway, and a number of onboard passengers. Then we formulate the action of each engine as a holding scale factor, which is used to scale a fixed maximum holding period. Finally, the reward function is defined to encourage the engines to balance the system of stability and control efficiency. Specifically, the first term indicates the inconsistency of headway among buses in the road. A larger series square indicates that the larger inconsistency among the headway among the bus, and which means there may be a heavier bus bunching. And the second term is used to penalize the control decision. This penalty makes sense because any decisions will introduce additional slack time or reduce the operational efficiency. And specifically, the dynamic process in this problem can be summarized as each bus will observe a state when it arrives at a bus stop and implement a holding decision that is determine the holding time. Then it will receive the feedback to evaluate its past decision at the next stop. Traditionally, the dynamic of multi-engine is regarded as Markov game, but this definition becomes inaccurate in bus control problem, since for each bus, there are a determined number of asynchronous control decisions between its two consecutive control. So then how do we achieve multi-engine reinforcement with such asynchronous issues? In private studies, most of them simply omit the issues and directly suggesting a classical reinforcement framework, the actor critic. Here, the actor is used to produce the holding action based on the local observation and is a parameterized function, which is usually modeled as a deep neural network. And the critic is used to evaluate the action of the actor, and it also can be modeled as a deep neural network. And the evaluation of the critic will be used to train the actor to learn a good policy in the system. However, this widely used framework is limited in our problem since it cannot take into account the undetermined impact from other engines. Specifically, that means that the critic cannot give an accurate policy contribution evaluation for each engine to learn an efficient control policy. As a result, we modify the classical critic architecture to handle the asynchronous issues by designing a novel critic network. This critic considers the overall impact after each engine's action in two parts. The first part is the ego engine, which is used to evaluate the actor's policy, and the event critic is used to account for the marginal contribution from other engines. To incorporate the undetermined information from other engines, we first introduce an event graph. Here the dashed lines indicates the bus trajectories, and we highlight 3 incoming edges as control event between 2 consecutive control of bus I during T and T plus delta. Then, inspired by inductive learning, we adopt graph attention network to develop the event critic to utilize the information from this event graph. Notably, we propose to separate a graph attention for aggregate information for downstream and upstream events respectively. Then the summation of them will generate the final result of event critic. In this case, the inductive learning will be more effective since we can encounter more scenarios when there are no upstream or downstream events. Then the target in this case, the target of the event critic is naturally a 0. And then the proposed inductive critic can be easily exampled into the classical at the critic framework, and for the critic, the objective function can be formulated as this. And here, the regularization term is used to encourage the inductive learning, because when there is no downstream or upstream events, there should be 0 contribution from them. And we adopt deterministic parsec gradient to train the parsec. And the goal of the actor is produced by the event critic. Is provided by the ego critic in this framework. And we establish simulation studies with some real-world data for the evaluation of the models. Specifically, I developed a simulation tech spec for the evaluation, and we first validate the simulation tech spec with some real-world transit data from an ancient city, and then there are 4 baselines for the evaluation, including no control and a traditional control method, and 2 reinforcement model based control method. And there are 5 evaluation metrics to evaluate the models in view of passengers and the transit system. First, we can say the training performance of of the reinforcement models. Here, we set the weight in the reward function as the 0.2 to place the priority on system stability. We can see that there 3 figures corresponds to these 3 items of this equation. We can say that the proposed method is more efficient to pursue larger reward related to the system stability, and this reward item is in particular related to the asynchronous insults. This validates that the proposed framework helps the engine learns a parsec to effectively optimize the system stability. Then we test the models by execution. First, we evaluate the models on trained bus lines. The left figure presents detailed stepwise performance comparison in different evaluation metrics. Overall, the results suggest that the reinforcement-based models are beneficial to efficient transit control. And we believe it is because of the long-term reward consideration and informative guidance from state definition. In particular, proposed model performs the best in stabilizing the system with the smallest average waiting time and average occupancy dispersion, while imposing more control interactions than the MADDPG and IAC, the other 2 reinforcement methods. The right figure shows the trajectory colored by occupancy. As can be seen, the real-world operation provides a challenging scenario with frequent bus bunching without any intervention. Notably, all reinforcement strategies seem to bring improvements at the upstream segments. However, we can see the proposed method clearly outperforms others in mitigating the heavy improving the heavy consistency along the entire operation. And we also validate the transferability of the model by evaluating them on untrained bus lines. For the 3 rows where the reinforcement models are not trained, we can identify that the transferability of these models. The result is similar to the trained rows. We can see that the proposed models again achieves best performance on system stability. The above transferability analytics reinforce the point that when under an asynchronous setting, the training process can clearly benefit from taking those uncertain events into consideration. And here comes the conclusion of this research. First, the reinforcement can play a better role in transit control with long-term consideration and state-dependent process exploration. Second, by considering the asynchronous setting in our model, the proposed framework presents better performance in both trained roles and untrained roles. And in the end, it's promising to apply such proposed models in other problems with similar spatial-temporal asynchronous issues. And for future study, I suggest promote robustness by taking into more uncertainty and abnormal situations. Also, how to achieve coordination control among multiple bus lines with multi-engine reinforcement will be an interesting topic. That's all. Thank you for listening and welcome for the questions.